Hello everyone, myself Amrish Bavsar, and I am here for the lecture series of structural analysis. All of you aware about the structural analysis. In that case, we had studied type of beam. All of you aware about that types of beam. That is first one simply supported beam, cantilever beam, overhanged beam, fixed beam, propped cantilever beam, and continuous beam. All of you had studied about the moment and shear force diagram, and that shear force and bending moment diagram is for the simply supported cantilever and overhang beam, because they all beams are determinate beams and remaining three beams are indeterminate beam that you had studied in structural analysis 1 in fundamental chapter. So you also aware about the fixed beam and propped cantilever beam, but now onwards you have to analyze the continuous beam, and we have lots of method for the calculating or else analyzing the continuous beam. In that case, first I am taking the introduction of slope deflection method, which is used for analyzing the continuous beam. So, as pointed out earlier, there are two distinct methods of the analysis of statically indeterminate structure depending upon how the equation of equilibrium, load displacement and compactability conditions are satisfied. For that, here two methods. First one is force method of analysis and second one is displacement method of analysis. In this module, the displacement method of analysis will be discussed. In the force method of analysis, primary unknowns are forces and compactability of displacement is written in the term of pre-selected redundant reaction and flexibility coefficient using force displacement relation. So all of you aware about the redundants and kinematic indeterminacy. It is most useful for the analysis of continuous beam using slope deflection method. For the solving this equation, the unknown redundant reactions are evaluated. The remaining reactions are obtained from the equation of equilibrium. It is most important thing, equation of equilibrium. In the displacement method of analysis, the primary unknowns are displacement. Once the structural model is defined for the problem, the unknowns are automatically chosen, unlike the force method. Hence, this method is more suitable for computer implementation. And in the displacement method of analysis, first equilibrium equations are satisfied. The equilibrium of forces is written by expressing the unknowns joint displacement in term of load by using the load displacement relation. These equilibrium equations are solved for unknown joint displacements. Three methods which are closely related to each other will be discussed. First one is slope deflection method, second one is moment distribution method, and third one direct stiffness method. So for the analyzing the continuous beam, we have a number of methods. In that, most popular methods are slope deflection, moment distribution, and matrix methods. This is stiffness method. Now, for the understanding of these methods, we must have to aware about the degree of freedom, right? That already we had studied in structural analysis 1 fundamentals. So in the displacement method of analysis, primary unknowns are joint displacement, which are commonly referred as the degree of freedom of the structure. It is necessary to consider all the independent degree of freedom while writing the equilibrium equations. These degree of freedom are specified at support, joint, and at the free end. For the example, a propped cantilever beam, which is shown in below, under the action of load P will be undergo only the rotation at B if axial deformation is neglected. Here we are always neglecting the axial deformation. In the case of kinematic degree of freedom of the beam is only 1, that is QB, means it is theta B, rotation at support B. In second figure, we have nodes at A, B, C and D. Under the action of lateral load P1, P2 and P, this continuous beam deform as shown in the figure. Here again neglecting 3 axial deformation. Now most important thing, instructional objective. Which are the objectives is used for analysis of this kind of continuous beam by slope deflection method? After reading this chapter, all the student will be able to calculate kinematic degree of freedom of continuous beam that we had studied, derive slope deflection equations for the case beam with unyielding support. Here we are always consider that supports are not yielding. Differential between force method and displacement method of analysis. State advantage of displacement method of analysis as compared to force method of analysis. Analyze the continuous beam using slope deflection method. So now in this lesson, the slope deflection equations are derived from the case of a beam with unyielding support. In this method, the unknowns, slope and deflections at the node are related to applying load on the structure. This is most important. As introduced earlier, the slope deflection method can be used to analyze statically determinate beam and indeterminate beam and frame also. In this method, it is assumed that all the deformations are due to bending only. In other words, deformation due to axial forces are neglected. The method as used today was presented by G.A. Mene in 1915 for the analyzing rigid joint structure. Here we are considering that all the joints of frame are rigid. Now deeply discussion about the slope deflection method and how we can get the end moments and how we can get the rotation. So from that rotation we are calculating common rotation at support, and from that we are getting bending moment. So for this problem it is required to derive relation between the joint and moment, that is moment at A to B and moment at B to A. Why we are choosing that? We know, suppose we have one fixed beam, and for that fixed beam we have two end moments at left hand support and at right hand support. Here we have continuous beam, and we are considering that this continuity of support is considered as a fix. So we, first of all, we must have to find out fix and moment from left to right and from right to left, that is moment at AB and moment at BA. In terms of joint rotation, also theta A and theta B and loads acting on the beam. For example, end moment AB denote moment acting at joint A of member AB. Rotation of the tangent to elastic curve are denoted by the one subscript. The following sign convention are used in slope deflection method. It is most important. We must have to follow these sign convention. First, moments acting at the ends of the member is counterclockwise direction are taken to be positive. The rotation of the tangent to the elastic curve is to be taken as positive when the tangent of the elastic curve has rotation in the counterclockwise direction from its original direction. Now, the slope deflection equations are derived by superimposing the end moments developed due to, first one, applied load, rotation of support A and rotation of support B. So in slope deflection method we must have to find out first fixed end moment, and we had studied the whole chapter of fixed beam. From there we can get the fixed end moment, and we have the specific equation for the end moment. It is depending upon the types of load. Here we have some standard cases of fixed end moment. We must have to memorize this equation. Without this equation we cannot get the fixed end moment, and it is the first step of slope deflection method. So let's try to understand the basic thing. If our both the supports are simple support or a hinge support, then chances of rotation should be there. But if our both the support are fixed, then rotation at the support is 0. So we can see in these figures, that is in fixed beam slope is 0, and in simply supported beam there is rotation at support A. Now what is slope deflection equation and how we can get that? The fixed end moments are required for various load cases. For ease of calculation, fixed end moment for various load cases are given at the previous slide. In the actual structure, end A rotates by theta A and end B rotates by theta B. Now it is required to derive the relation relating to theta A and theta B with the end moments, that is moment AB and moment BA towards this end. Now consider a simply supported beam acted by the moment MAB at A and the end moments MAB deflected the beam. The rotation from their theta A and theta B are calculated from the moment area. It is also we know from this calculated equation is like this: moment at AB is equal to moment of fixed end MFAB plus 2 EI upon L in the bracket 2 theta A plus theta B minus 3 delta upon L, and moment from B to A is equal to fixed end moment from B to A plus 2 EI upon L 2 theta B plus theta A minus 3 delta upon L, where fixed end moment is used. Rotation at support. If our support is simple, then rotation A or rotation at B are there. But if support is fixed, then theta is 0. Here deflection is also there, delta. What is that delta? If our support is sinking due to force, then delta is there, otherwise delta is 0. So, application of the slope and deflection equations to statically indeterminate beam, the procedure is to be same where the applied beams or frames. It may be summarized as follow. Identify the kinematic degree of freedom as we discussed for the given problem. This can be done by drawing of deflected shape of the structure. All the degree of freedom are treated as under, which unknowns in the slope deflection method. Determine the fixed end moment at each end of the span to applied load. The table given in the end of this session. Express all the internal end moments in the term of fixed end moment and near end and far end joint rotation by slope deflection equation. Write down the equilibrium equation for each unknown joint. For the example, at the support in the continuous beam, the sum of all the corresponding moment to an unknown joint rotation at the support must be 0. In our next session, I will describe these equilibrium conditions, and after that we can consider one simple example and analyze that continuous beam. Solve these above set equilibrium equations for the joint rotation. Now, substituting this joint rotation in the slope deflection equation evaluated at the end moment. Determine all the rotation, and that rotation is put up in the equation of end moments, that is slope deflection equation. Thank you. We will discuss the whole example in our next session.